Hello there, this is a tutorial on solid-phase peptide synthesis using the CEM microwave-assisted peptide synthesizer. The peptide synthesizer uses an organic synthesis technique pioneered by Dr. Robert Bruce Merrifield called solid-phase peptide synthesis. This technique allows for the synthesis of peptides that are difficult to express in living systems, and most importantly, allows for the introduction of unnatural amino acids. Even at short lengths of 3 or 4 residues, we start to run into difficulties when using the liquid phase peptide synthesis techniques. If we simply tried to synthesize the peptide we wanted by adding in every single residue it is composed of, we can't be guaranteed at what order these residues will attach to each other. Therefore, we can assume that every permutation of arrangement could be present in solution. Circumventing this issue using a liquid technique would require repeated ligation and purification processes between each addition of an amino acid to the growing peptide chain. If our addition reaction and purification results in lackluster yields at each step, the end result is we will have a low yield for the peptide we are trying to produce. But what if there was a vessel on which we could originate our growing peptide chain? And what if this vessel was insoluble to the solvents used in each reaction step? Now we can distinguish our peptide chain from all the other things that we have added into the reaction vessel. This is the fundamental idea of solid-phase peptide synthesis. Instead of a solution reaction, beads that are small, insoluble, and porous are treated with functional linkers, where peptide chains can be built. If we saturate the reaction vessel with protected amino acids, we can wash the beads after the reaction has occurred. This will result in our growing peptide chain being attached to the beads. The growing peptide chain will not develop unnecessary repeats because the protection group is there. This group can be removed by additional reagents, and another cycle can be repeated until we get our desired peptide sequence. After we've attained the desired peptide sequence, we can cleave the peptide off of the solid resin support by adding a solution of trifluoroacetic acid and other scavenger ions. Now let's look at the instrument's interface. We can start by inserting a sequence. Click on the Sequence button, and then go down to the desired name. From there, we see a list of previously stored peptide sequences. There are buttons for the 20 common amino acids, as well as buttons for external amino acids the user can add. Create a new sequence by clicking on the directory you want the sequence to be stored, then click the button New Sequence. Name the peptide, and then insert the sequence by clicking on the amino acid buttons provided, from N-terminus to C-terminus. You can also type the sequence out on your keyboard using the one-letter codes. The sequence can be renamed when needed. Make sure to always save if you made any modifications that you'd like to keep. Now that the sequence is inserted, we can make a respective method file that will customize each step of the synthesis for the specific sequence. This is especially useful for residues that need different parameters than the default, such as lower temperatures or longer reaction times. Click on the Methods button. In the Methods column, click on the folder which you'd like to store the method, and then click New Method. Name the peptide, and then go to the Sequences column and select the peptide in which the method will be applied to. As you can see, the default methods have already been applied to each residue in the peptide. The peptide synthesizer is pre-programmed to couple specific amino acids in specific ways. For example, histidine is coupled at a lower temperature. Any changes to the specific step can be made by using the drop-down menu. In addition, there are options to enable UV monitoring at each step, as well as a final deprotection of the last residue, which is enabled by default. In the resin information section, we can tell the instrument what scale we want our reaction to be in this case 0.1 micromolar. For resin substitution, I must first explain what it means. Any resin we buy commercially will have a substitution number on the label, the units being milliequivalents per gram. Higher substitution numbers mean that there are more peptide equivalents per gram of resin used. This means that there are more peptides per bead of resin. This can be beneficial when we want to use less resin and get more peptide. There will be more peptide on each resin bead. However, such crowding might cause longer sequences that are more difficult to synthesize to fail. For the long sequence case, we will want to use a low substitution resin, in which there are lower amounts of peptides per gram resin. Now that we understand resin substitution, how can we translate that to actual amounts of resin needed for the synthesis? One of the best aspects of the peptide synthesizer is its ability to calculate reagent composition. Here, we can click Calculator followed by Reagents, and the first default tab is Resin. We can enter the scale of our reaction in millimolar, as well as the resin substitution number found on the labels. Once we click Calculate, we're outputted a number which is the gram of resin we need to weigh out and insert into the reaction vessel. The following tabs contain all of the reagents used for reactions, including deep protectors, bases, activators, amino acids, and even the cleavage cocktail. For example, in the Activators tab, clicking on the activator used will show a calculator in which the concentration or volume can be changed, and the weight will change respectively. This is useful for quickly knowing how much to weigh out when a concentration changes or when a volume changes. What if we have set up our reaction, but we don't know if we have enough reagent? Luckily, the calculator can also calculate how much reagent is used for any specific method. Click Calculator and then Usage. Select any method that you are planning to run and click Add Method. This could be multiple methods. Then check the desired methods. The calculator outputs weights and volumes of each reagent used in the method. This can be especially useful for reagents that are running low, but you don't know if they're going to run out. There's even a checkbox for the UV worst case volumes, for when the UV detector decides to repeat any specific cycle. Speaking of cycles, now we can get down to the nitty-gritty and really see what goes on in each step. Click on the Cycles button, and we will be introduced to a column with 4 folders. In the first folder, called Resin, is the method used to introduce the resin into the reaction vessel. The general gist of the resin step is to transfer the solid support resin into the reaction vessel. There are multiple rinse and transfer steps to ensure all of the resin is transferred into the reaction vessel. Next comes the amino acid tab, which shows a subdirectory of the scales of the reactions that we can perform. Let's click a specific cycle we can use. This one is the 0.1 millimolar double couple with 50 degrees Celsius temperature. Let's break down some of these steps. First, we see that the reagent for deprotection is added, followed by the microwave method. This deprotects the amino acids. What we have in the reaction vessel now are resin beads with multiple growing peptide chains attached to them, which are now deprotected at the ends. This deprotection allows for the next residue to be added on. Following the deprotection are multiple wash steps. These wash steps are necessary since the deprotection step detached multiple protecting groups into solution. These protecting groups in solution must be washed out. After these wash cycles, the deprotected peptide chain is ready to receive the next residue. The next step is where the following amino acid is added. This is followed by adding activator reagents, as well as using the microwave to promote the reaction. Because this is a double coupling cycle, amino acid, activators, and microwaving are repeated once more. Observing these columns, we see that modifications can be made to any aspect of the reaction. This amount of customization is also present in cleaving as well as final deprotection. If we want to take fancy to a new level, we can click on the default button and make sure that every time there's a cysteine in the sequence, we apply a specific method to it. So now that we've set up our cycle for exactly what we want, we've set up the defaults, and we know what reagents we're using. Now all we have to do is set up a real reaction. So here's a quick example. Prepare all the amino acid solutions that pertain to the peptide being synthesized. Each amino acid has a specific marked bottle for the solution to be made up in. The specific weight needed will be dictated by the scale of the reaction and can be found out using the reagent calculator. N-methylpyrrolidinone, or NMP for those who can't stand tongue twisters, is the general solvent that we use for the reactions. All reagents, including amino acids, activators, and deprotectors, all use this as their solvent. Make sure the amino acid is fully dissolved in the solvent through vortexing. Then place a filter on the feed tube of the amino acid you're about to attach. Now attach the amino acid bottle. Creation and attachment of activator and activator base, as well as other reagents, go through the same process. The instrument also needs a constant supply of NMP and dichloromethane. These solvents are attached to the side of the instrument through pressurized caps that attach to the solvent bottle directly. The resin is also loaded onto a plastic tube and solvated with NMP. These beads are insoluble and swell up in the solvent. The resin is attached to the resin feed tube without a filter, since the resin needs to be transferred into the reaction vessel. After a few runs, 3 inline filters have to be switched out in order for solvent to flow smoothly. These filters are screwed in from each side. Here's a quick recap of the steps needed to synthesize a peptide on the software side as well as in the lab. We've created the sequence we want in the sequence editor. We also created a method that matches the sequence and accommodates for any hard-to-attach amino acids. If we wanted to, we can modify a multitude of parameters such as volumes or solvents used for any specific step. In the laboratory, with numbers from the reagent calculator, we've created solutions of amino acids as well as steep protection and activator. We also made sure that the instrument has enough supply of NMP and DCM. We make sure that everything is attached, including the solvated resin in the resin feed tube. We double check to make sure everything is okay by using the usage calculator to make sure that we have the right volume of solutions needed. Next, we make sure that all the filters are relatively new. Finally, we drag the method into the number corresponding to where the resin is attached. Then we can press the start button and finally start our reaction. This concludes the tutorial. There are other aspects of peptide synthesizer which weren't covered in depth, such as maintenance, which needs to be performed frequently on the instrument in order to keep it in running condition. The peptide synthesizer also keeps logs on anything that has occurred in previous runs. These logs are not mentioned in the tutorial but are available to the user. The computer attached to the instrument is set up for remote monitoring via programs such as TeamViewer. Steps to setting up remote monitoring via the internet can be attained through any group member working with the peptide synthesizer. Finally, any questions can be answered by referring to the manual or asking any group member that has had prior experience with the peptide synthesizer. Thank you for watching this tutorial.